So it's my great pleasure to introduce Matthew Ballard and he will give the lecture about rationality and exceptional collections for toric varieties. Okay.
Thank you for the introduction, and thanks to the organizers for inviting me. So I guess I should also thank all the participants who are many hours ahead of us on the East Coast here. Hopefully I can keep you awake. So what I'm going to talk about today is joint work with Alex Duncan, who's from South Carolina also, Alicia Lamarche, who's currently in Utah, and Patrick McFaddin, who's at Fordham. And you can copy down the archive numbers here if you want to look through some details a little bit more. Okay. So there's two basic ways in which we can use derived categories to say something about rationality. The first way is to see if some property of the derived category can obstruct rationality in some way. So if I phrase it in some type of moral form, some of the projected variety is not rational, the derived category is too complicated. So it can be made precise in some questions. The most maybe well known of that is Kuznetsov's conjecture about two different things. So in this case, not too complicated means it's not the derived category of a commutative variety. Okay. So what I'm going to be interested in is I'm going to be interested in the other direction. Okay. Can some property of the derived categories force rationality to be, or maybe a weaker form of rationality? We already have a conjecture we mentioned before, the Orlov. And I should also mention here, there's a refinement of this, strengthening of this. At least what I found is in once. And this says if the derived category has a full exception collection, that implies that X is rational. Okay, so what evidence do we have for such a thing? Well, there are no counterexamples. That's a good start. Right? In the case of showing a particular class of varieties with exceptional collections is rational, Brown and Shipman worked over C and showed for surfaces with strong full exceptional collection line bundles, the surface was automatically rational. And then over a non-closed group, Vial showed that if you were geometrically rational over the separable closure, then in fact, and you had a full exceptional collection, in fact, a numerical full exceptional collection, then you were in fact rational over the base field itself. Okay, so let's look at some variations on this. So I could ask, instead of rationality, I could ask for stable rationality. I could ask for retract rationality. I could ask for unirationality. Or I could just ask that it has a point of numerality. Just to remind everyone, so stable rationality, if I cross with some copy of affine space, it's going to be birational to some other affine space. Retract rational, I have rational maps in both directions, affine space and on some open set. Unirational, so I have some finite unit, and then rational point of all. You know what we're talking about. Okay. So of course, if we know Orlov's theorem holds, or Orlov's conjecture holds, then this cascades down. Right? It's rational that cascade down. So what I want to look at also is a form of Orlov's conjecture that is very natural over non-closed fields, and that's based off of looking at exceptional objects that instead of just being the ground field as the endomorphisms, we're going to allow the endomorphisms to be separable extensions of the ground. So the terminology I use is a tall exceptional for such things. So if you want to compare this to the usual definition of exceptional, well, if you're actually over the separable closure, then it's just the same as we talked about before. There's no extension. In general, if I base change such a thing, it's going to split. Let's say I indexes the isomorphism classes in the summands. Each of the EI will be exceptional objects. And then the Galois group will act up to isomorphism on these exceptional objects. So really, when I talk about the tall exceptional, it's talking about over the separable closure, the usual notion plus some action. Okay. And a simple example, if you want one, is just blow up a C point and plenty of over arm. And that exceptional divisor will give you such an object. Okay. So, just to repeat the previous list, if we assume instead of exceptional, if we assume it's a tall exceptional, then are we guaranteed that it's rational? Are we guaranteed that it's stably rational? Retract rational, irrational, has a rational point? Or, since in multiple choice tests, it's good to throw in the none of the above option for the students. Why don't we throw that in here and see how we go? Okay. So one thing to note is that we can make silly counterexamples without a little bit of assumptions on the variety itself. So what we're going to assume that X geometrically is irreducible. Okay. And if you believe, I mean, you could ask, like I said, you can ask these questions for just exceptional objects, right? And if you believe Orlov's conjecture, and, I think given the evidence we saw this morning from Sasha's talk, there's certainly a healthy give and take about what the expectations are for this. So if it's not rational, is it stably rational always? It doesn't have a rational point. We're land somewhere in between. Okay. So the answer to this is, in fact, none of the above. So what you can produce is you can produce a smooth, projective, geometrically irreducible threefold over the rational numbers that has a full tall exceptional function, but doesn't have a point over T. So some remarks before we continue. So we could ask, what if K is not equal to T? Can I do this for a general thing? Well, I don't want to be closed, of course. But maybe I want to do it for general number field period. So what do we need that's ingredients to go into this base that depend on the field? So what do we need? We need a field extension that's biquadratic. I'll talk a little bit more about that in a minute. And then there's an invariant of tori that needs to be non-managed. And I'll talk more about that. It's going to come a little bit later in the talk. So if you want to forget you saw this part. feel free to get yourselves. Okay. So these aren't too hard to produce. And we'll see in a minute, maybe in a half hour or so, how they are produced. Okay. So you could then ask yourself, maybe having a rational point was the only obstruction. Maybe if I had a rational point, I was, and a full Étale exceptional collection, I was automatically rational. Just that rational point is obstruction. It's the only obstruction. So you can ask whether this is a quasi-trivial problem. So, and the answer is at least down to retract rationality. The answer is still no. So there exists a non-retract rational, smooth projective, geometrically reducible threefold over the rational numbers that has both a full Étale exceptional collection and a rational. Okay. And all we need over the field here is we just need that. The extension is biquadratic. Okay. Easy to produce. Assuming you're not ruled out by some properties. Okay, so before we keep going with what we know, maybe delve a little bit into what we can guess and suppose. So maybe if you have a full Étale exceptional collection and a rational point, maybe you need a rational question mark. Rank, supposition, just to find a question that you can think of. Okay. So now I'm going to go into the construction of both X and Y. And then in the end, I'll circle back to Orlov's original conjecture. And these constructions go through the class of toric varieties, but toric varieties are non-closed fields. So if you were to think about toric varieties, perhaps in the most familiar form, you've seen letter C, you would think I have a fan. From that fan, I'll build torus orbits, and I can glue my torus orbits together. So there's not much to rationality for those things, and their exceptional collections always have, but their derived categories always have full exceptional collections by result on. And you can write down an algorithm that basically produces the full exceptional collection from some line for the toric variety. Now, over a non-closed field, things get a little more interesting. So first, let's just remember, a torus is just going to be an algebraic group that, if you base change sufficiently, becomes a split torus, some power of G. And here, remember, I'm taking Q bar to be the separable closure instead of anything more fancy. And I'm going to take this geometric notion of what a toric variety is. When it used to toric varieties, maybe you didn't see them as things, you were handed them as varieties with an action of a torus, where you have an open copy of that torus inside, and the action is the extends the left action. So here we'll just say it's a normal variety over the field. It's going to have an action of T, and it's going to have an open dense orbit for that action. We'll usually only be, well, here we'll only be interested in smoothly projected toric varieties. And it's important to keep in mind, now I say T toric variety because there is some ambiguity just saying toric variety. So if I drop the T, I'm really saying that either the T is clear from context or there is some T, and you can find it. So to contrast with the familiar case, if T is just itself some power of GM, then we're going to say T and X are split. We'll call them both split. Okay, and the split ones, those are the ones that will give us things. Non-split, there's nothing. So, what are some nice examples? Simple examples that will be enough for us today for Toric and Toric varieties. Well, for Toric, if I want to take one step beyond GM and its powers, then I can look at the restriction. So the torus whose K points are the L points of GM. And then that's pretty simple as the torus. So we take a little bit one more step in the construction, and we can talk about the normal torus and things that are a little more interesting in terms of thinking, a little more variety, what we get out of its rationality. So here, this is the norm map for our field extension, and we're just looking at the current. So if we take our favorite field extension, maybe this isn't field, but the simplest one for three things. Is the complex numbers overall. Then the Bay restriction is just C star, but we think of it as an odd value. And the norm one torus is ES1 in that, right? Because it's just the things of norm equal to 1. In a sense. Okay. And you can see this is a different thing than G1. Okay. So as I mentioned before, you can have multiple toric structures on a single variety. So P1, the projected line over the real numbers. Well, you have your familiar R star toric structure. Dilation. And then you also have the structure of an S1 toric variety. So how do you get that? Well, you can look at messed up a sign, which is essential. So this guy here is isomorphic to P1R, but I have a big open after where I set Z equals 1, where I got some, and you can check the action, multiplication extension. The whole thing. Okay. So, about the simplest toric variety of multiple structures. Okay. Back down here. Continue. One that I get if I make the sign error that I had before is this quadric, which is also an S1 toric variety. It doesn't really matter. The sign is -1 or 1. Yeah, I think so too. But the big difference here is that, of course, there are no rational points, no real points, excuse me, for this toric variety. Okay. And I'm going to want to separate out the notion of a toric variety that has a point from one that doesn't. So the ones that have points of the ground field are called neutral. And there's a nice result of theological Vosper-Brzezinski that allows me to identify in a way that depends only on the torus when I have a K point for a smooth projected toric variety. So I have a K point overall if and only if I have a K point in the open orbit. Okay, so we draw some pictures then. So in general, I'm going to have this open orbit sitting inside my T toric variety line. And this is going to be a T torsion. Okay. And what the previous result, Kryachko and Boskrzinski, is saying that I have a K point for Y overall if and only if the torsion I have inside of Y is the trivial torsion. And this gives me a way to make new T toric varieties out of old ones. What I can do is I can just cut out the torus and glue in the torsion. So precisely, let's say I'm given a neutral X, a T toric variety, and I'm given a T torsion, U. Well, we can make another T toric variety is by taking the contracted product. So I set Y to be U cross X, and then we divide by the diagonal, almost diagonal, action of T cross. And so this gives us a way to assign to torsors of T forms of X. And now, if we want to think about this over the separable closure, then we want to get back to a familiar picture of fans. And I already gave a little hint before. When we talk about fans, we're going to talk about, when we talk about, sometimes they're called arithmetic toric varieties to avoid confusion with the split fans. But when we talk about toric varieties with non-closed fields, we're really talking about, after we base change to A bar, we're talking about fans with some finite group action induced by the Galois action. So, let me say the picture over K bar. All right, so you know that over K bar, we just get the usual torus. Okay. And the Galois group acts by skew linear automorphisms on this torus. And if I just look at my nomials, where they go, the characters, basically, then this will give us a homomorphism from the Galois group to invertible matrices of size R by R. Just the action on the nomials of our torus. Okay, so you can deduce pretty quickly now that if you fix R with only finite up to isomorphism 4i, and if you know all the subgroups, the conjugacy of G, L, R, and Z, then you know all the Torah in some principle. In particular, you can go backwards. So let's say we're given such a thing. We get an action of our Galois group on our split guy, and hence by descent, we get something, which is check to be a torus, over the base group. Okay. So that's really what the data of the torus is over the separable closure. Now, if you want to talk about what a toric variety is, so there's some fan over the separable closure. And really, if we're acting on the toric variety, then we're moving torus orbits to torus orbit. The Galois action can't unmake a torus orbit. Can't change the dimension. So what we have is a little bit more constrained homomorphism. In this case, we land in the automorphism of the fan itself with our action. Okay. So, fun one to draw. I can draw it. Is this guy? Okay. So it's a natural S3 cross using my QZ action. And then if I can locate a fan with a finite group action, identify that finite group action on the induced lattice as coming from finite group coming from the Galois group, then I can produce a toric variety over my base group along the same lines. Okay. And now some rationality properties are well known for tori, and it's neutral toric varieties. So again, T is a torus, X is a smooth projecting neutral toric variety, and G is the Galois group. And I don't want to write Galois. So it's a theorem put together by results of a few people that you can pick out exactly when T is stably rational by looking at the Picard group over the separable closure of the toric variety X. So it's stably rational if and only if that Picard group is stably a permutation module. So let's say P is the shorthand for the Picard group. What we're asking is P plus, oops, no arrows. Is P plus some free module, so here, A and B are G sets. Is P plus some free G module, isomorphic to another free. Okay. And the answer for the Picard group of this action, Galois group, is yes. And in fact, the torus is stably rational. And then it's retract rational if instead of requiring that you sum with a free G module, you just require that it's a summing. So if, in this case, P plus G is 0. Okay. And now rationality itself is still a subtler question. One well-known open question about rationality of tori that you would think, well, I don't know what you would think, but it's at least simple to state. So we can look at the norm 1 torus, except for, well, in the particular case of an extension of finite fields. Okay. Is this always rational? You can check that it's stably rational, but it's still unknown whether it's always rational. And it has interesting implications, like a certain efficiency of compression in torus-based cryptography that was developed about a decade ago. that can be bypassed a bit, but okay. So to summarize, stably rational, retract rational are well known. They can be checked in terms of some linear algebra plus the loop action problem. Rational itself is something that takes a loop and is more of a case-by-case thing. Even so, in low dimensions, we have almost all the answers. So we have to go up to dimension 3 before we identify any non-rational tori. Oops. And then in dimension 4, things get a little more interesting. We can have rational, we can have stably rational, and we can have retract rational. And there's a little bit of ambiguity between where that line is drawn. In fact, despite what I wrote here, it kind of implies. I think it's still an open question whether you have a specific stably rational but non-rational torus. Okay. So, takeaway from this is, unlike in the split case, we have a little more variety. We have some but it's not, whatever we study rationality is not true. And tori being the simplest of algebraic groups, you should be able to say useful things in a broad sense, both geometrically and homologically. Okay. So if we want a simple example of a torus that is not retract rational, such an example goes back to Alicia Lamarche in the 60s. And that comes from this biquadratic extension. So just a reminder, if the Galois group is just Klein-Fold group, then we say we have a biquadratic extension. Oh, sorry. Then the norm 1 torus, recall that it sits inside this short exact sequence. If we take characters, we look at G modules, and what do we get? Well, we just get one Z many characters of GM. We get the group ring for the Klein-Fold group as the characters of our biquadratic extension, and then we have some co-kernel of this. The map here is just 1 goes to the sum of the line. Okay. So from this, you can tune out a little bit and play around with bases or matrices, whatever you want, to write down a presentation of what M looks like with its Z mod 2Z cross Z mod 2Z action. If you want a specific example, one that we'll see in a second as useful, you can take Q adjoin root 5 and root 20. Seems like overkill. Why don't we do 2 and 3? But if we think back to the original theorem, there was an extra condition. The 5 and 29 come into play to make sure that that makes the condition satisfied. All right. So that gives a sense of what the rationality of tori and toric varieties looks like. Either you don't get a point, In that case, there's some torus for the torus you have. You can cut out that torus or put in the torus, okay? And then you can ask, well, is that thing actually rational? It's always unirational. And you have these criteria, the stably rational and retract rational. And you know, you can work a little harder and you can check, is it rational or not? Okay. So let's turn now to what questions we can ask for the derived category. Like I said, our expectation over C, over a closed field, is that we have full exceptional collection. It's very simple derived categories. So, do we have a full exceptional collection over a general field for a toric variety? No. You can see pretty quickly this is going to imply that if I take the Picard group over the separable closure, this is a trivial G-mark. Right? Just take the determinant map from K0. K0 is a basis. For our exceptional collection, there's no Galois action because these are just copies of K. And it surjects onto the card. So there's no action. I think you get a sense that this is a very special class of toric varieties over a non-closed field. Those that have trivial Galois structure for their card groups. Now, maybe we can get away with a full étale exceptional collection. And the answer is still no in that case, but we have to do a little bit more. So in that case, we take this Q, this quadrant that I gave before that had no rational points. It has a semi-orthogonal decomposition into a copy of O, and then a rank 2 vector bundle, which I'll just call V. And the endomorphisms of V are isomorphic to Hamilton's quaternions. In particular, they're not commutative and not commutative. Call this V field. I'm not going to complain. So, if this were to have a full étale exceptional collection, then in fact you can conclude that the endomorphisms have to be commutative for every exceptional object. And this is a basic application of this idea of non-commutative motives, an explicit presentation of the category of non-commutative motives for separable algebras over a field K. That's given by Ballard. And this particular application to Severi-Brauer varieties, not just Severi-Brauer curves, is Rationality. Okay. So we can try again. Let's include a point, and let's ask that we have a full étale exceptional collection. Okay. The answer is unknown, but most likely not. So here, the non-community of any exceptional object or division algebra, it's not going to help us, but it's sort of more a basic problem. There's a conjecture of Mercury and that asks, if I take this K0 of my split toric variety, is it a permutation module? Or the automorphism group of the fan? Okay, so if it's a permutation module for the automorphism group of the fan, then you get a Y action factor for those automorphisms. And now you have a basis that's permuted by the Galois action. And if you have a tall exceptional collection. So expectation here is this is probably not true. It seems realistic that you can some computer tell you exactly. But So now, given that we've talked a little bit about the background for rationality and the background for derived categories of Toric varieties, let's return to the main result and start constructing the varieties X and Y. So you can guess that they're related. And first we want to construct X. Okay. So the construction of X starts with a full exception collection on a particular split Toric variety that's stable under the envelope syndicate. And this was produced by Castrovet and Tevelev. And we only need the Toric variety corresponding to the root system A3. What does this exceptional collection look like? If I remember correctly, we have 6 line bundles supported on divisors, Toric divisors. These correspond to the middle weights in the root system. And then we have 20 line bundles. And so we have O. My count must be off. We have 19. Good thing this is recorded. So you just count by the number of A1 and A2 root subsystems inside A3. We got 6 of these. We got 4 of these, but then for each of the A2 root systems, there are 2 line bundles I have to pull back. Right. And then there are 3 more you have to throw. So that's what it's called. They call these the custom. Okay. So it's not all line bundles, but it's not too far off. It's some divisors with line bundles on there, and it's a line bundle. Okay. And if you read the paper, well, you translate the paper from the language of moduli spaces to corresponding Toric variety, you can see that they're explicitly described in terms of gathering system itself. They're varying under anything that is written. Okay. So the next bit that we need is we need to know that these exceptional objects actually descend to Étale exceptional objects on any neutral form. It seems reasonable to expect that there's no non-Étale exceptional objects and no exceptional objects with division algebras. If we have a point, but that's still something we can prove. Okay. So things of this form that are basically have lifts to the Cox ring. If have lifts to the Cox ring, then you can check that they descend fine no matter what on the top. And then you have to figure out what torus you want. And as I mentioned before, the simplest torus we have is the one where we have biquadratic extension. So you can find a subgroup of the automorphism of the family associated with A3 of automorphism in the root system of A3, such that the associated H module for that subgroup is isomorphic to the group of characters for a biquadratic extension. So if you did the exercise from before, you can see, here's a basis for this, and then you can write down a similar basis here and check that you have I found the right basis and actually say. Okay. So what we have here, right, so here means we get a neutral Toric variety over K. For the torus, that's just the norm 1 torus of this biquadratic extension. And this lemma here says we have a full Étale exceptional collection. And remember that this torus is not rational. It's not stably rational. It's not even retract rational. So we have our variety that has a point with all exceptional reflection, and is not rational. And all we needed to input into this really was just that there exists a biquadratic extension over the base field. Probably can't do this in dimension 3. You can do this any higher dimension, like crossing. Okay. So that's X. That's the neutral form. Now what we want to do is we want to construct Y. So Y is the one that told us we aren't even guaranteed the existence of a rational point if we have a fully tall exceptional function. And the goal to do this is we want to find a non-trivial torsor for our norm 1 torus so that we can twist the Étale collection as we twist the variety. So we twist with this non-trivial torus, we remove any rational points, and then the Étale collection just twists over to another Étale collection on Y itself. So there are 2 questions you can ask about how to do this. The first is, if I have a torsor for my torus, can we twist a general element of the derived category? Well, we don't have to answer that in full generality, but it's a good question to think about. And then if we can twist it, is there a guarantee that what we end up with doesn't become non-commutative? So if we think back to Q, our quadrant without a point, our quadrant curve, then that is a twist of a torsor of the projected line. And the usual exceptional collection that we have over P1 of R, over norm 1, it doesn't twist completely. O does, of course. But with O1, you have to add it to itself once, and then you can twist it. But once you take the endomorphisms of the twisted object, the vector bundle in the other form, you end up with a ring of non-commutative elements. Non-commutative ring. Okay, so we'll just briefly address each of these 2 questions as we go through this. So if we have a linear algebraic group acting as the projected torque variety, and if E is Étale exceptional, then there always exists some positive R, so that direct sum power of R is twistable for any G torus. And so the idea is what we want to do is we want to linearize some of this with respect to the G action. So it's not so hard to move equivariant objects when I twist by a torus. We just want to check that some power of it is actually secretly equivariant. Okay. So that takes care of the first question, that we can twist these things. And the next question, well, we want to know that the endomorphisms we get when we twist our exceptional object don't end up becoming non-commutative. And we can be a bit more ambitious. We can ask, well, are there torsors that do not show up whenever we try and send the set of torsors into Brouwer invariance, H2 of an Étale algebra over G? And that's what this set here is defined. You can think of it as all torsors invisible to all Brouwer invariants. Okay. You can make definitions what you want, but you actually hold a handle on what this looks like. So we can describe this for a general algebraic group G in a concrete, more compact fashion, using the idea of a cold-flash resolution. But let me just stick to tori for facts right now, because this is what we use. The first one we don't really use. The second one we do, because there's always computations for the right sign. So first one is that you can check that G of blank T, the functor from field extensions to whatever the base field are, is actually stable by rational invariant torus. And it's trivial if and only if the torus is in the track direction. So it means that there's some extension where it's non-zero. It means that the torus is not in the track rational. That's nice. And then if you restrict your attention to just number fields, this invariant is familiar. It's the Tate-Shafarevich group of the torus. Okay, so you can, for a general G, it looks pretty close to this, except that you need to take into account the behavior of the real places, which is not a problem for Tori. Not interesting Tori. We've seen what Tori are. Okay, so now we've got to build Y. So like we said, we got X and before. We just need to construct a biquadratic extension over Q. I gave you an example. That was Q adjoin root 5, adjoin root 29. This is over Q, this is biquadratic. And now we want to compute it, which reduces to computing its Tate-Shafarevich group. That's known. In fact, I took this from an example in Brzezinski's book. Associated one torus. It's not trivial, it's Z mod 2Z. Okay, so we take some, I'll just let T be the torus because I don't want to keep writing all that out. We take, that'll be 2. We take the non-trivial torus inside here, and then we set Y to be the contracted product of this torusor with X. And we know that since it's a non-trivial torus, there are no points in the open stratum, there hence no points anywhere. And if I think about the function that takes in a torusor, E prime, and spits out the endomorphism algebra over this contracted product, after I twist my exceptional object, this is a cohomological invariant. Forgot to mention the exact definition if you're not familiar with them, but it's just a functor from the category of field extensions. Okay, that's a natural transformation between functors in the category of field extension. That looks pretty natural. So it's a cohomological invariant, and from our definition of G, we know that whenever we apply any Brouwer invariant to a torusor, it ends up being trivial. So the endomorphism algebra we started with is the endomorphism algebra we end up with when we twist our exceptional object, our exceptional collection over Y. So that gives us the Étale exceptional collection on Y, and that gives us the counterexample. So if you think of, another way to think of it is if you talk about dimension as a simple invariant, as a way to capture the complexity of the derived category, and you say, okay, well, my category is built of dimension 0 things, so dimension 0 things. Can I say anything about how it behaves with regards to rationality and something? You need some information on how complex actually how wonky it is. So that's a negative answer So you might think, well, what happens if we come back to Orlov's original question? If I kill the Galois action, and you've seen that's a fairly strong condition on the Toric variety. If I kill the Galois action on the Picard group with a separable closure, am I guaranteed that I'm rational? And in that case, the answer is yes. And it's not terribly hard, in fact. It's already known to Voskerinsky once you rephrase it in terms of a torus that has a presentation as some. So there's a torus that's a Bay restriction, and the torus we're looking at T is the kernel of a subgroup that's isomorphic to some composition here. And such tori are rational. So there exists implies T is rational. And this exact sequence just comes from the fact that the card group is true actually. So before I finish, I just want to invite everyone, if we haven't already been invited. We have 2 virtual conferences coming up that I'm helping to organize. One of them is the first week in November, and you might notice that on Tuesday in the first week in November, we're going to have some rather interesting things going on in the United States. So if you want people to, if you want someone to commiserate with, there's a good chance. And if you want some interesting mathematics, that's good. So if you want more information on these, or you want to figure out how to get invited, just you can reach out to me. You can find my contact information on my webpage. You can find more information about events and then some other events that I'm organizing. So thank you very much. Hopefully I took your way.
All right, thank you, Matt. Any questions? Yeah, if not, let's proceed at 5 o'clock with a talk by Greg Perlstein. Thanks again, Matt.
Thank you.